Okay, so I have never done a screencast, so hopefully this works okay, but I want to walk through these pretty fast. So let's get started. I'm going to use blue arrows to be my incident rays and red arrows to be my reflected rays. So for this top left one, we're going to start with our incident ray, which is parallel to the axis. Then we're going to have our reflected ray, which goes down through the focal point like that. Then the next incident ray is opposite, it goes through the focal point, and that reflected ray is opposite and goes parallel to the axis. Our third incident ray is going to go through the center of curvature all the way down, and then that reflected ray goes back up exactly the same path. So as you can see now, all three of our red lines, all three of our reflected rays have one intersection point, and that is going to give us the image. This image is inverted. It's inverted, which means it's also real because it's on the front side of the mirror, and it is reduced because it is smaller in height than the original image, or the original object. All right, these next two are going to be similar but not identical to the one we just did, so let's get started. All right, here we are on the center of curvature. The rules are going to be exactly the same. We have our incident ray is parallel, reflected ray that is through the focal point, then we have incident ray through the focal point, reflected ray that's parallel, then we have for this one, we do not have another ray at this point because you can't really have a light ray that goes through the center of curvature when you're on the center of curvature. So our image is just going to be at that intersection. Now, ideally, if all my lines were perfect, this would actually be directly under the original object. That is only true when you are at the center of curvature. So the things we can say about this image for sure are that it is inverted and real. It's kind of difficult to see in this picture, but when you're at the center of curvature, it should technically be, the image should be exactly the same size as the object. Let's move on to the next one where we are between the center of curvature and the focal point, so we're going to do parallel through the focal point, through the focal point, parallel. Now here, if you try to do a ray that goes through the center of curvature, well, that ray is never going to interact with the mirror. Okay, well, let's try to do a ray that's lined up with the curvature that goes upward instead. Okay, well, that also doesn't interact with our mirror. So again, like the one before this, we're just not going to worry about that ray in this case. So we're just going to do our image at the intersection of the two reflected rays that we have. Again, this image is real and inverted. Again, it's kind of hard to see the size, but this is actually enlarged. The image is bigger than the original object. Questions on a quiz or a test, I will try to make sure they are more like the top one up here, where it's pretty extreme and easy to see. All right, the next one is a strange case, so let's go ahead and look at that one. All right, so we start this one like we would any other one. We have our incident ray that's parallel, then we have our reflected ray through the focal point, then we have, well, we can't do one through the focal point, so we'll go to incident ray through the center of curvature. Well, that line doesn't interact with our mirror, so let's do one that's lined up with the center of curvature and goes up. Okay, that interacts with the mirror. And so now that one's going to bounce back exactly through the center of curvature. And here's where things get strange. These lines are parallel. They are never going to intersect. What that means is that there is no image formed in this case. You may actually remember this from the notes. I told you originally that if your object is on the focal point, that is a blind spot for a concave mirror, and you will get no image. It is also mathematically correct to say that these lines are going to intersect at infinity, so you could either write no image or image at infinity. Moving right along to the next one, here we have a case where you are between the focal point and the center of curvature. So we're going to do our incident ray, and then our reflected ray, here, if you do this incident ray, then it doesn't interact with the mirror, so we're going to line up with the focal point but go the other way. So then we do incident ray, reflected ray, and then last but not least, again, line up with the center of curvature but go towards the mirror. Then the reflected ray goes back the other way. Now, here are our three reflected rays. They do not intersect anywhere in real space, but this does not mean that we don't see an image. Our brains are kind of dumb, and they don't understand that light can bend. So when your eyes pick up those three rays of light there, it assumes that they must have traveled in a straight line, and it thinks back to where those would have come from if they did travel in a straight line. We represent that with dashed lines. So we're going to make dashed lines that we extend back behind the mirror from each of our reflected rays. The point where these dashed lines intersect is where your brain sees the image. So your brain sees an image right there. Now again, there is not actually anything there. Your brain is just making it up. Because your brain is making it up, we refer to this as a virtual image. So this image is virtual, upright, and enlarged. All right, this last one is an example of a convex mirror. It is the only one on this page that we have worked that is a convex mirror. However, its answer is pretty similar to the last concave one that we did. So let's go ahead and get started. Convex mirrors are a little bit tricky because the focal point and the center of curvature are behind the mirror, but we have to remember that the mirror is a solid object. Light does not pass through the mirror. So we're going to set up our incident ray here. Our incident ray is parallel and it only goes as far as the mirror. Now here's the problem. Our reflected ray, it's tempting to put our reflected ray like this to the focal point, but light does not travel like that. Instead, we line up with the focal point, but draw our reflected ray up like this. All right, so now we do the same thing for our next incident ray. Our next incident ray is lined up with the focal point, but it actually only travels as far as the mirror. And then its reflected ray travels straight backwards, parallel. The final incident ray is lined up with the center of curvature like this, but it only actually travels as far as the mirror. That reflected ray travels backwards along the same path. So again, here we have three arrows that never intersect in real space, but our brains think that they traveled in a straight line, so it extends those rays back behind the mirror as dashed. We're going to represent that as dashed lines, and where those three arrows intersect is the image. So here's the image. And then in this case, we will categorize this image as virtual. So it is virtual, it is upright, and it is reduced. I think I got distracted because someone came in my room, but in the previous one it was virtual, upright, and enlarged. So those are the 6 example problems. If you notice, we did 5 example problems that were concave and 1 example problem that was convex. This is because all convex mirrors create virtual, upright, reduced images. This answer that we got for the 6th one is the only possible answer for a convex mirror. But please, please keep in mind that there are a ton of possible answers for concave mirrors.